Soviet engineers dreamed of a spaceplane that could take off like a rocket and land like an airplane. The Mikoyan-Gurevich MiG-105 was the first prototype in the secret spiral program, designed to challenge the limitations of orbit and reentry. Pilots would glide back from orbit with precision, testing the cutting edge of aerospace engineering. Every flight was a test of materials, heat shielding, and human courage. This tiny spacecraft carried the hopes of an entire nation during the Cold War. Its shape was unconventional, its missions dangerous, and its technology decades ahead of anything in the West. The MiG-105 was not just a plane or a spacecraft, it was a bridge between the two. In this documentary, we reveal how it flew, what it achieved, and why it remains a legendary experiment in spaceflight history. The MiG-105 was born from the Soviet spiral program, a response to the United States X-20 dinosaur. Engineers envisioned a reusable spaceplane capable of orbital flight and atmospheric landing. Its mission was to test controlled reentry and gliding techniques. The design challenged both material science and aerodynamics. The MiG-105 would bridge the gap between aircraft and spacecraft. Its distinctive shape resembled a wedge or lifting body. This allowed for stability during hypersonic reentry. Heat shielding covered the nose and leading edges to survive extreme temperatures. The spacecraft relied on careful airflow management to stay controllable. Every curve and panel had a purpose in flight. A single pilot would guide the MiG-105, though early flights were unmanned. Controls had to account for both orbital dynamics and atmospheric aerodynamics. The cockpit was compact but sophisticated. Life support, navigation, and reentry systems were integrated in one module. Every instrument was critical for mission success. Engineers faced immense technical challenges. High-speed reentry generated intense heat and stress on the airframe. Materials had to resist both thermal shock and structural deformation. Redundant systems were tested to prevent catastrophic failure. The MiG-105 pushed the limits of Soviet aerospace engineering. Testing focused on lift-to-drag ratios and stability during descent. Small-scale models flew first, followed by full-scale atmospheric prototypes. Data collected informed guidance, control surfaces, and heat shield improvements. Each flight added to the knowledge base for future orbital vehicles. Spiral engineers iterated quickly on design and procedure. The program remained shrouded in secrecy. Even within the Soviet Union, only select engineers and pilots knew the full scope. Information was compartmentalized to prevent leaks. Western intelligence only glimpsed the program through fragments. Yet the MiG-105 symbolized Soviet ambition in space. The first MiG-105 prototypes conducted atmospheric glide tests before any orbital flight. Engineers wanted to understand control and stability at high speeds. Pilots reported unusual handling due to its lifting body design. Every descent was carefully monitored by telemetry. Data from each flight shaped the next iteration. Flight tests pushed the MiG-105 to extreme angles of attack. The lifting body allowed for controlled gliding even at hypersonic velocities. Control surfaces had to compensate for airflow changes continuously. Pilots relied on precise inputs to maintain stability. The results amazed engineers who had feared instability. High-speed reentry was simulated using drop tests from helicopters and ballistic rockets. The spacecraft endured temperatures far beyond conventional aircraft limits. Heat shields proved essential in protecting structural integrity. Sensors monitored stress and thermal gradients in real time. Each test refined the design for future orbital missions. Navigation systems were continuously improved. Pilots practiced precision landings, testing gliding trajectories. Accuracy was essential to ensure recovery in remote areas. Instrumentation allowed engineers to analyze performance meticulously. The MiG-105's guidance systems were revolutionary for its time. Unmanned test flights complemented crewed trials. These flights eliminated risk to pilots while gathering crucial data. Autopilot and feedback systems were tested rigorously. The aircraft responded dynamically to atmospheric and aerodynamic changes. Engineers learned how to integrate automation with pilot control. By the mid-1970s, the MiG-105 had completed multiple successful test flights. Stability and control were proven within the program's operational envelope. Lessons from these flights influenced future Soviet reusable spacecraft designs. The Spiral program's research laid the groundwork for orbital maneuvering. The MiG-105 demonstrated the feasibility of controlled reentry. The MiG-105 featured a lifting body shape unlike any previous Soviet aircraft. Its wedge-like fuselage created lift without traditional wings. This allowed for controlled glides at hypersonic speeds during reentry. Engineers experimented with materials capable of surviving intense heat. Every component balanced weight, strength, and thermal resistance. Forward-swept surfaces enhanced maneuverability during descent. Airflow patterns were carefully modeled to prevent turbulence. Heat-resistant alloys protected structural joints. Advanced control surfaces corrected instability instantly. The MiG-105 relied on precise engineering to succeed. The cockpit was compact but sophisticated. Flight instruments integrated navigation, life support, and reentry data. Pilots needed to monitor multiple systems simultaneously. Safety systems included redundancies to prevent catastrophic failure. Training was intensive and focused on split-second decision-making. Its thermal protection system was groundbreaking. Nose and leading edges used ablative materials and heat-resistant coatings. Sensors measured temperature and stress across the airframe. Data collected informed future Soviet spacecraft, including orbital designs. Every flight provided critical insights into reusable heat shielding. The MiG-105 also pioneered advanced guidance technology. Pilots combined manual control with automated feedback systems. The aircraft could correct trajectories autonomously. This reduced the risk during extreme reentry conditions. Spiral engineers used this data to improve future orbital vehicles. Structural innovations extended to the landing system. Retractable gear was designed for precise runway touchdowns. Shock absorption had to accommodate high-speed glides. Engineers tested materials for both strength and weight efficiency. The landing phase proved the vehicle's versatility. Ultimately, the MiG-105 was more than a spacecraft, it was a flying laboratory. Its lessons went beyond any single test. Aerodynamics, materials, and avionics were all refined through experimentation. The program proved that controlled reentry was achievable. The MiG-105 set a precedent for future spaceplanes. Flight testing pushed the MiG-105 to its limits. Pilots executed glide paths that simulated orbital return. Sensors monitored structural loads and heat distribution. Engineers refined both guidance and control systems. Each flight improved knowledge of atmospheric reentry. Unmanned tests reduced risk while gathering critical data. Autopilot systems corrected flight path deviations instantaneously. This ensured precision and reliability in extreme conditions. Redundant control systems added a layer of safety. The MiG-105's success depended on perfect coordination of hardware and software. High-speed drop tests validated lift and drag performance. Aerodynamic performance exceeded expectations in several maneuvers. Engineers collected precise measurements of airflow and pressure. Data informed the design of subsequent Soviet spacecraft. Controlled gliding proved possible at previously unimaginable speeds. The program also advanced pilot training and procedure development. Pilots learned to interpret real-time data rapidly. Simulated orbital reentry prepared crews for future missions. Emergency protocols were designed for worst-case scenarios. These lessons informed later reusable vehicle programs. International secrecy limited knowledge of the program. Western intelligence only detected fragments. The Spiral program remained largely unknown outside the USSR. Yet its technological achievements were significant. The MiG-105 quietly influenced the global understanding of spaceplanes. Even with limited flights, the MiG-105 demonstrated the feasibility of reusable spacecraft. Lessons extended to avionics, flight control, and materials. Engineers applied these insights in other Soviet projects. The aircraft was a stepping stone, not a destination. His contributions shaped future aerospace research. By the program's end, the MiG-105 had accomplished its mission. Controlled atmospheric reentry had been proven repeatedly. Automated and pilot-assisted systems worked together seamlessly. Engineers gained confidence in both lifting body designs and guidance technology. The aircraft had fulfilled its purpose as a technological pioneer. The MiG-105 remains a symbol of Soviet aerospace innovation. It proved that small, experimental spaceplanes could test extreme flight conditions. Lessons learned influenced the design of later reusable spacecraft. Engineers mastered lift, heat protection, and automated guidance. Its legacy continues in modern spaceplane programs. The Spiral program, though secret, demonstrated remarkable ambition. Its concepts pushed material science, aerodynamics, and avionics. Controlled orbital reentry became more feasible because of it. The MiG-105 bridged the gap between theoretical design and practical testing. Soviet engineers achieved what once seemed impossible. Pilots and engineers collaborated under high-risk conditions. Every flight balanced human skill with machine precision. Their work expanded understanding of spacecraft control during reentry. Knowledge gained informed Soviet approaches to orbital maneuvering. The MiG-105 became a laboratory in the sky. Technological innovations included automated flight corrections. Computers monitored instability and adjusted control surfaces instantly. This approach foreshadowed later spaceplane designs worldwide. Pilots could focus on critical decisions while systems maintained safety. Spiral engineers pioneered a new era of flight. Even though the MiG-105 never became operational, its influence is undeniable. Reusable spacecraft concepts adopted lessons from these tests. Lifting body research informed both Soviet and later international designs. The program validated simulation, materials, and flight control integration. Its knowledge continues to guide aerospace engineering. The MiG-105 also highlighted the value of experimentation under extreme conditions. Engineers accepted high risk to gain breakthrough insights. Controlled failure became an essential tool for innovation. The aircraft expanded the limits of what a spaceplane could achieve. Its legacy is measured in knowledge, not deployment. Ultimately, the MiG-105 was a milestone in spaceplane history. It transformed ideas into data and possibility into understanding. Its flights proved that a small experimental craft could teach lessons far beyond its size. Spiral engineers set the stage for modern reusable spaceplanes. The MiG-105 will always be remembered as a pioneering step in human spaceflight.